Okay, Assalamualaikum and a very good afternoon. So let's have a look at a few examples on Bode plot. Okay, the first one, let's have a look at a transfer function given by this equation. So in order to plot a Bode plot, so first you need to write down the equation into a standard form. So in which you need to have the constant and also the component with s outside or inside the bracket. So this is for the constant k0. So the equation, you have to factorize the equation so that the s will be added by 1. Okay, so in this case we took out the 100 as the factor, so the equation yields s divided by 50 plus 1 in the bracket. So now the 100 will be included in the constant equation. So in this case, you get the standard form transfer function with k0 as the constant, and you have the components on top and at the bottom. So next you need to write down the individual transfer function. So first we have the constant 20 log 10 of the constant 1 over 100 equal to minus 40 dB. Next we look at the numerator. We don't have any s or outside the bracket or inside the bracket, so no zeros. So followed by the denominator, so there's no s outside the bracket, so no poles at origin, so you only have single s inside the bracket, so you have poles at 50. So this is, don't forget, for poles equation, so it must be 1 divided by the component s divided by 50 plus 1, so you have 1 poles or real poles at 50. Okay, next let's sketch individual components based on the individual transfer function that you have derived earlier. So first one, start with constant. So you need to sketch both the magnitude and the phase plot. So for constant, negative 40 dB, so this is H1S, so you have negative 40 dB. So you just have a constant of k0 in dB, so it is negative 40. And in terms of the phase plot, theta 1, so when it is a constant, so the phase will be 0 across the omega values. Okay, next move on to the second component that we have, real poles at 50. So first one, for real poles you have 0 until 50. So for the magnitude, so it poles, so it is decreasing negative 20 dB per decade, so until 50. So you have 0 until 50, and then you have negative 20 dB per decade slope. Okay, so this is your H2 as magnitude across omega values. And about the phase, so when it is pole, so again negative trend, so at 50 it must be negative 45, and then you extend the graph to the earlier decade and the next decade, and the rest will be 0. So this is your theta 2. So this is negative 90, and here is 0, and here is omega. And finally, you need to sum the plot. So in order to sum the plot, so you need to combine all sketching inside one graph. So this is for the magnitude plot. Okay, so you can break the section into decade. Okay, so for start with the constant, you have negative 40 dB. Negative here is negative 20. Here is negative 40. So you have negative 40 dB line. So this is your H1S, the constant, and then you have the real pulse H2S. Okay, so it is 50. So you can start here with maybe 5, and then here is 50, and here is 500, and so on. So here is 0.5. Okay, so it's 0 until 50, and then decrease by 20 dB per decade. So 20 dB for the first decade, second one, and so on. Okay, so this is your H2S line. Okay, next, sum them up. Okay, to sum them up, you need to look at the reference line. So the first reference line is at 0, and then you total the lines by decade. Okay, so the first one, look at from 0.5 to 5, 0.5 to 5. So you have a 0 slope. This is 0 value, and then plus negative 40. So 0 plus negative 40 equal to negative 40. Okay, same goes to 5 to 50. Okay, so then from 50 to 500. Okay, so you see that's negative 40. And then you have the decreasing slope. Okay, so you can look at the endpoint at this point. So it is negative 20 plus negative 40. It is negative 60. So negative 60 somewhere here, negative 60. So the line will go drop down until negative 60. So the same trend continues onwards. Okay, so this is the summation, the magnitude summation of the transfer function. Okay, so this is your HS, the main transfer function. Okay, so this is the magnitude plot of HS. Okay, how about the phase plot? So now the phase plot, you have 0. Okay, here is 0. It's omega, so this is for the theta. Okay, you have 0 for the constant, and then you have only one line for pulse at 50. So here use the same line, will be much easier. So here is 50, so at 50 it is negative 45. Okay, so and then extend to earlier and next decade. So negative 90, so it's negative 90, and extend to earlier decade. So you'll get the green one. Okay, and this is your phase plot for the given transfer function. Okay, let's look at the second example. So given the transfer function as the equation shown, so again, to plot a Bode plot, you need to rewrite the equation into standard form. Okay, in standard form, you need to break the components into constant and the S components. right? So this is for the constant K naught. So you'll see the stand as a constant here, and then you have single s, meaning you have zeros at origin, and then at the bottom inside the bracket all s must be added by 1. Okay, so the first one, s divided by 1 plus 1, so this is poles at 1, and then the second one you need to factorize 100 because you need to have s plus 1, so factorize 100, so the component become s divided by 100 plus 1. So now you need to move all constant values into constant equation. So finally, this is the standard form of the given transfer function. So you have the constant and the components both on top and at the bottom. So next you need to rewrite individual transfer function. So first you have the constant 20 log of your K naught. So K naught in this case is 10 divided by 100 equal to negative 20 dB. And then move on to the next S on top. So there's no bracket, so you know it is zeros at origin. Sorry, supposed to be zeros at origin. Okay, so this is zeros at origin, and the transfer function for this component is h2s equal to s, followed by the third component. So you have poles at 1, so real poles at 1. So this is not, although it is crossing at 1, but it is not equal to poles at origin, because when you have poles at origin, the equation will be 1 over s only. Okay, so next you have the fourth component, so s divided by 100, so you have poles at 100. Okay, now let's sketch individual component. Okay, so the first one is the constant, so negative 20 dB, so you sketch negative 20 dB constant. So this is your H1s, negative 20, and for constant the phase will be 0. And then for H2 at the second component, H2s equal to s, so zeros at origin. So when it is zeros at origin, you have the positive slope by 20 dB per decade crossing at 1. So we can assume something like this. Okay, so 20 dB per decade. So here is negative 20, here is 20 dB per decade. And when you have zeros at origin, the phase will be constant 90 degree. Okay, so the third component, you have poles at 1. So poles at 1, so the line will be zeros until 1, and it is poles, so it's going down by 20 dB per decade. And then for real poles, so poles, it is negative 45 degree at 1, extend to the earlier positioned and next decade, and the rest will be 0. Okay, and lastly H4, you have poles at 100, so it will be 0 until 100. So poles downtrend, so it's going down by negative 20 dB per decade. And how about the phase at that frequency, so it is negative 45, extend to the earlier and next decade, and the rest will be 0. So here is negative 90, negative 45, and 0. So maximum is negative 90 degree. Okay, so once you have all the individual plots, then you need to sum them up. Let's sum the magnitude of the transfer function. So you need to sketch individual transfer function in the same graph before you can sum them up. Okay, start with H1s. So it's a constant of negative 20 dB. So this is H1s. And then you have H2s equal to s. So it is zeros at origin. So origin is 1. So the line crossing at 1 with positive 20 dB slope. So this is H2s, and then H3 you have the pulse at 1. So meaning that it can mark at 1. So pulse 0 until 1, and then you have pulse negative 20 dB slope. So this is H3. And then H4 you have pulse at 100, so mark 100. So it's 0 until 100, and then negative 20 dB slope down there. Okay, so this is H4. So in order to sum them up, so you need to look at point by point and total the magnitude of the component crossing at the same omega. Okay, look at the first one. Okay, so at omega equal to 0.01. Okay, so you have the first one is 0, omega 0.01. So you have 0 plus the yellow one plus negative 20, and then plus the blue line negative 40. So it is negative 60. So mark negative 60. And then at 0.1, okay, at 0.1, so you have this line, so it's 0 plus you have the blue lines, the magnitude is negative 20, and then you have the yellow line, it's negative 20, so it is negative 40. And then at 1, so at 1 here, okay, so you have magnitude of 0 plus crossing at 1, so negative 20, so it is negative 20. At 10, so you have crossing at 10, so you have here is 20 plus here is 0 plus negative 20. Okay, negative 20 for the yellow line, and you have another one, the purple one, negative 20 plus negative 20. So altogether 20, 20 is negative 20. So it's negative 20 again. Okay, at 100, you have this one. Okay, so you have 40 plus 0 plus negative 20 plus you have the purple one is negative 40. Negative 40. So it is negative 20. And then at 1000, so again you have here predicate, so it is 60 plus the yellow line, negative 20, plus the green line is negative 20, and then plus the purple line, negative 60. So negative 40, negative 40. So negative 40. And then you will see that the trend goes on. So you can see the same decrement. Right? So that, then just connect the summation. So you get the black one as the summation of the individual transfer function, and this is your HS. Okay, now let's sketch the summation of the phase plot. So again, you need to sketch individual phase plot on the same diagram. So first one, you have the constant, so it is 0 degree. This is H1s, and then H2s, it is 0 at origin, so it's 90 degree constant. And then you have poles at 1, so at 1 it must be 45 degree. It pulls, so it's negative 45 degree, and then extended before and after, and the rest will be 0. And lastly, the fourth one, another pulse at 100, so at 100 it must be negative 45 extended to the previous decade and next decade, 1000 is there. Okay, so and then previous and after must always be 0. Okay, so now let's sum them up just as the magnitude summation. So you need to consider point by point. Start at omega equal to 0.01. So let's use purple colored for the summation. So at omega equal to 0.01, you have 90 degree, and then plus 0 degree, so it's 90 degree. And then at 0.1, you have 90 degree plus 0, again 90 degree. And then at 1, omega equal to 1, you have 90 degree. And then plus 0 is 90 degree. Minus 45 is positive 45. Okay, and at 10, you have 90 degree. And then plus 0, minus 90, so you get 0. And then at 100, it's 90 degree. Plus 0 is 90, minus 45 is 45, and then minus 90, it's minus 45. Okay, look again at 100, it's 90 degree, plus 0, plus minus 45, plus minus 90. So here, so it's minus 45. And then at 1000, you have 90 degree plus 0, and then 90 degree plus 0, and then minus 90, and then minus 90 again, plus minus 90. Why 290? Because you have the dark blue lines minus 90 and the light blue color minus 90, so you get minus 90. Okay, so now connect them all. Okay, there you are. Alright, so next, if you continue until next cycle, 10,000, so it's 90 plus 0 minus 90 minus 90, and it keeps minus 90 onwards, so then it's constant over there. So this is the purple one is your HS. Okay, this slide basically represent the same example as earlier, but this is when you draw. Okay, when the question asks you to draw a Bode plot, meaning that you need to use logarithmic graph paper. Okay, if the question asks you to sketch, so you can use earlier technique. Okay, just sketching in blank page. But if the question asks you to draw a Bode plot, so you need to use logarithmic graph paper to plot. Okay, so don't forget that the logarithmic paper divides the section by decades. Okay, so first label the x-axis, the omega, by decades. So you can just adjust either to start with 0.01 or you can start at 0 and so on, but it will be much easier if you separate them by decades from the beginning. All right, so next, draw the constant. Okay, the k, and then you have the zeros. You have zeros at origin. Okay, crossing at 1, and then you have poles at 1. Okay, and lastly you have poles at 100. Okay, finally sum them up. Okay, just as the one that I have discussed earlier, but in this case you use the logarithmic paper. Okay, same goes to the magnitude plot. First you need to define the x-axis, the omega, indicate, and then plot the zeros at origin is constant 90 degree, and then you have poles at 1, so it's crossing minus 45 at 1. Another one, poles at 100, it's 45 minus 45 degree at 100. Finally you total them up. Okay, let's have another example, example 3. So as usual, you need to write the equation in standard form. Okay, secondly, you need to write individual transfer function, and thirdly, you need to sketch individual transfer function or frequency response. Fourth, you need to sum them up. Sum the magnitude and the phase. Okay, so just use the same step as previous example. So I just briefly discuss the standard form. So HS, this is the first step, equal to, break them into constant, and then the components. So make sure that all s must be added by 1. Okay, so here the first one, s divided by 1 plus 1 divided by the bottom one, you have s, single s, so you have poles at origin, and then you have s divided by 100 plus 1, and don't forget to take out the 100. Okay, so in this case, now you can write individual transfer function. So h1s is the constant, so 20 log of 10 over 100. So you get your answer in dB. The third one, you have the first transfer function. Next you have zeros at 1. Okay, so you have zeros at 1, so the equation is s over 1 plus 1. The fourth one, you have at the bottom 1 over s, so this is poles at origin. So remember, origin omega equal to 1, and then you have poles at 100, so h4s equal to 1 over s over 100 plus 1. Okay, so once we have all the individual transfer function, then you need to sketch the frequency response for each individual component, both the magnitude and the phase plot, and then finally sum them up. Okay, if the question asks you to draw, then you need to use logarithmic paper to plot or to draw your Bode plot. Okay, this is basically the solution for example 3 using logarithmic paper. So you can compare with your sketching. So please complete the Bode plot sketch before you look at this drawing. So first you have the constant, and then you have zeros at 1. Okay, zeros at 1, so the line at 1, 0 before 1, and then positive 20 dB per decade from 1 onwards. And then you have poles at origin. So poles meaning that decreasing slope by 20 dB per decade crossing at 1. Okay, this is the poles at origin, and lastly you have the poles at 100. So at 100, poles at 100. Finally you sum them up. Okay, same goes to the phase plot. First, you have poles at 100, so it's negative 45 degree at 100, extended to earlier decade and next decade. And then you have poles at origin is negative 90 degree, constant. And then you have constant, and you have zeros at 1. So zeros at 1 is 45 degree positive at 1, and the rest extended to earlier decade and after, next decade, and finally you total them up. Okay, this is another example, but just using sketching. You just sketch the Bode plot of the given transfer function. So this is the given transfer function. So as usual, you need to derive the individual transfer function, and then sketch the individual frequency response, and finally total them up. So this is basically sketching of all the components, and this is the summation of the magnitude plot, and this is the sketching of the phase of the individual components. You can see that H2, H3 and so on representing individual phase, and this is the summation of the phase of the given transfer function. Okay, please try this out. You can also draw the frequency response on the logarithmic paper. With that, thank you.